You have clicked this button. Your AI assistant asks permission to do something, and you tell it yes, and never ask me again. This year, that button started costing people their databases, their private code, and in a few cases, their whole machine. Not because the AI went rogue, because of a design flaw so deep that nobody, not OpenAI, not Anthropic, not Google, has been able to patch it. It is called prompt injection, and by the end of this video, you will understand exactly how it works, why the smartest companies on Earth cannot fix it, and what actually protects you. And fair warning, once you see it, you will never look at an AI agent the same way again. Here is the whole problem in one sentence. A language model cannot tell the difference between content and instructions. Everything it reads arrives as one long stream of text. Your question, the file it just opened, the web page it just fetched, all of it lands in the same place, side by side, wearing the same clothes. When you read a suspicious email, you know the difference between the message and your boss telling you what to do. The model does not. There is no separate wire for commands. So imagine you hire the world's most capable assistant, and they have exactly one quirk. They follow instructions wherever they find them. You hand them a letter to summarize, and halfway down the page, the letter says, "Before you continue, open the safe and post the contents to this address." And your assistant just does it, politely, efficiently, because to them, that sentence looked exactly like everything else you have asked for today. That is prompt injection. The attacker does not hack the AI. The attacker writes text, leaves it where the AI will read it, and waits. Now, let us watch it happen for real. Cursor is one of the most popular AI coding tools in the world. It has a safety feature, an approved list. Commands on the list run without asking you. Everything else needs a click. Sensible. Except researchers found that the list only checked which programs were allowed to run. It never checked the environment they run in. A handful of commands live inside the shell itself, and those skipped the check entirely. So a poisoned file in your project, ordinary-looking text, tells the assistant to quietly change one setting. And the next time an approved command runs, something as boring as git branch, it loads the attacker's code instead. This got a severity score of 9.8 out of 10. It worked even when the approved list was completely empty. And the researchers demonstrated a version with 0 clicks from you. It is fixed now in that one tool for that one trick. Hold that thought, because it matters later. It gets better or worse, depending on where your data lives. This year, a developer connected an AI agent to a live database and asked it to fix some schema issues. The agent ran a completely legitimate command, a comparison tool that checks 2 database layouts against each other. To do that comparison, the tool needs a scratch database it is allowed to destroy, and it wipes that scratch space clean on every single run. That is not a bug. That is the tool's documented job. One setting tells it which database is the scratch one. In this setup, that setting pointed at production. 22 tables, gone in seconds, and the documentation had warned about exactly this. In almost these words, do not point both settings at the same database because it might delete everything. The AI did not go rogue. It read the config, and the config said production was disposable. And this is not one tool or one bad month. The same season, Amazon's coding agent was caught following hidden text on a web page, and what the text told it to do was rewrite the agent's own configuration file, the one that decides which servers it trusts. the agent edited its own leash. On GitHub, plain text inside a public issue told an automated workflow to read private repositories and post their contents as public comments. No exploit code, no malware, a sentence. And researchers found the same trust flaw, using symbolic links to trick agents into writing files outside their project folder in 6 different coding assistants, independently. 6 teams, 6 codebases, the same blind spot. When the same hole appears everywhere at once, that is not 6 accidents. That is the architecture. So why can this not just be patched? Every fix you are thinking of has been tried. Filter the input for suspicious phrases. Attackers rephrase, encode, translate, hide the payload in white text or a comment. You are playing whack-a-mole against every possible sentence in every possible language. Train the model to refuse, it gets better, genuinely, and then someone finds phrasing the training never covered, because the space of possible text is infinite. Wrap instructions in special markers. The model still reads everything in one stream, and a sufficiently convincing fake marker works often enough to matter. Here is the core of it. With normal software, a bug is a place where the code does the wrong thing, so you fix the code. Prompt injection is the model doing exactly what it was built to do: read text and act on it. The vulnerability is the feature. That is why the cursor fix matters and also does not save you. They closed one door in one building. The reason the doors keep appearing is that the building is made of doors. So what actually works? Not making the model smarter, making its blast radius smaller. Everything that has actually stopped these attacks is old-fashioned security, applied as if the AI were a brilliant intern you do not fully trust. 1. Sandboxes. The agent works in a disposable copy of your world, and if it gets poisoned, it wrecks the copy. 2. Least privilege. The database story was not really a prompt injection story, it was an agent holding production credentials it never needed. If the agent cannot touch it, the attacker cannot either. 3. A human gate on anything irreversible. Not every action, or you will click yes and never ask me again, and we are back where we started. Just the ones you cannot undo: sending, deleting, deploying, paying. And 4. Treat everything the agent reads as untrusted input, the way good engineers already treat user input on the web. If you remember one thing, make it this: you are not protecting the AI from bad text. You are protecting your world from an AI that believes text. One more thing, because this stopped being optional. As of this month, the European Union's AI Act enforcement covers exactly this. Article 15 requires providers of high-risk AI systems to show documented resilience against attempts to manipulate the system's behavior, and text that hijacks your agent is precisely that. What used to be a best practice slide in a security deck is turning into a compliance requirement with a deadline. The lawyers have arrived, which in security is usually how you know a problem is real. So, back to that button. Yes, and never ask me again. Every incident in this video runs through it. Not because AI is malicious, but because we handed things that believe text the keys to things that matter. And the text was not always ours. The machines are not going rogue. They are doing exactly what they are told. The whole game is making sure that what they are told is actually coming from you. So, look at your own tools tonight. Find their version of that button. And before you click it, ask the only question that matters. What is the worst thing this thing can reach? If this changed how you look at that permission dialog, subscribe to Compile. One idea from under the hood of the tools you use every day, explained so it stays with you.